Okay, so thank you for the introduction. I'll be talking about circuit QED, circuit quantum electrodynamics, and geometric phases. So as hinted at by the title, I'll start with a brief introduction to circuit QED and show you some basic experiments you can do with it. And then I'll move on to what I've been doing during my PhD so far, namely measuring geometric phases in this setup. So it's work which has been done mainly at ETH Zurich in the group of Andreas Waldraff. And we've had some theory support by Stefano Pugnetti from the Scuola Normale Superiore in Pisa. And just if you have questions, feel free to interrupt. Thank you. For the start, a few words about cavity quantum electrodynamics. It's the study of the coherent interaction of light and matter. So the basic components of such a setup are the following. We have a mirror, which forms a cavity. And then inside this cavity, we have a photonic field. And what we do then is we add atoms which will fly through this field and interact with it. Now, the system is described by a few parameters. The most crucial one, I would say, is G, which describes the coupling strength between the atom and the photonic field. And then you also have kappa, which is the decay constant of this field. So it will tell you how long a photon lives before it gets out of the mirrors and leaves the cavity. Lastly, if the atom is excited, after some time, the excitation will be lost. It will decay to its ground state, and thereby emitting a photon. And gamma is the decay constant of this atom. So what we want to do is get those parameters in the right regime so that we can do something like quantum computation or quantum optical experiments. So that was a traditional setup with mirrors and optical photons. What we have is a little bit different, and it's called circuit QED. So we replace the mirrors and the cavity by a superconducting resonator, this meandering line. So we have microwave photons living in there. And we don't have a real atom flying through the cavity. What we have is something static. We have in here, in this little green box, an artificial atom, which is, by all means and purposes, a system with many levels which we can address. This is a zoom in of this artificial atom, and this particular type is called a transmon superconducting qubit. And what we do is basically quantum mechanics on a chip, because we can fabricate this with pretty much standard E-beam and photolithographical techniques, integrate it on a PCB as shown here, and connect it to some microwave lines which we use to manipulate the system and read it out. Now, you might ask, how does this work? Well, let me start out with classical circuits at first. So we have a little toolbox with capacitors, inductors, and resistors. One of the simple things we can build with this is an LC circuit. This circuit will have a resonance frequency, omega of 1 over the square root of LC. And because we want microwaves, we use approximately 5 gigahertz as a resonance frequency. Since it's a harmonic oscillator, the energy spectrum will look like this. You have equidistantly spaced levels. But because we want to qubit, we want to single out 2 levels so that we can address them selectively. So we need our computational subspace. Because it's harmonic, we have some trouble, so it doesn't really work like this. We need to change something. And this is why we go superconducting. So we add something to our toolbox. This device called a Josephson Junction. It's an inductor, but it has a special property that it's nonlinear. So when we take our LC circuit and replace the inductance by such a Josephson junction, the energy level spectrum will change. It'll look like this. We have the ground state and the excited state, which are set apart from the higher states. And we'll use those two bottommost states as the logical states of our qubit. Now this Josephson junction, its inductance depends on phi, which is the phase difference of the condensate wave functions of the Cooper pairs on either side of the junction. Before talking a bit more about the Josephson junction, I should mention that when I say we have two levels, it's a bit of a lie, because actually we have higher levels. So we not only have G and E, the qubit, but we also have the F level. And we can use those three states as a Q-trit. And now I would ask you to keep this at the back of your mind. So whenever I say qubit, I'm hiding a part of the truth, and sometimes when we do experiments, we have to remember that we have higher levels, and if we want data which nicely fits to the theory, we need to take those into account. It will pop up later in the talk. Now a few words about Josephson junctions. It's a device which is composed of two electrodes, which are superconducting. And those electrodes are separated by a thin oxide layer, which will cause, which allows Cooper pairs to tunnel from one side to the other side, thereby forming a superconducting current, I, across this junction. Now, because it's superconducting, you can describe the Cooper pairs here by a condensate wave function, which has a certain phase phi I on this side, and a certain phase phi 2 on the other side. Now, the relevant quantity describing the dynamics of this system is the phase difference across the junction, phi 2 minus phi 1. Then Brian Josephson has shown that the supercurrent flowing across the junction is I naught, the critical current times this phase difference. So when you exploit this I and compute the inductance, it flows in and it gives you this nonlinearity, which allows you to build a qubit. Now it's possible to use this phi as a quantum number for your qubit. What we do here with our transmon type qubits, we use the conjugate variable, so we use the charge as a quantum number. But before we can start, we need to initialize our qubit. So somehow we need to put all the excitation in the ground state. To do this, we need to cool it down. So take our circuit, here at room temperature. Then we couple it to some control circuit. So we have some coaxial lines and some microwave generators, which we use to control it. Then when we were done with manipulating it, we need to read it out. So on the other side, we had some more cables, a chain of amplifiers and filters, and in the end, some detection. So typically, we use FPGAs to measure the signal. Now to cool it down, the first step is to avoid dissipation. So we make it superconducting. To achieve this, we place it into a dilution refrigerator and cool it down to approximately 10 millikelvin so that everything is in the ground state. And to avoid even more excitations from the outside world, we make sure that the coupling is pretty weak between the exterior and the quantum circuit. So we add circulators and insulators and other thermalizations to those lines to make sure that there is no thermal population left inside the quantum circuit. So I've been talking about this charge type of qubit. So this transmon device, which was invented in Yale in 2007. But you could use other variables. So you could use a flux qubit. And the qubit is then defined by the flux which threads the superconducting loop. Or you could also use the phase. To describe the system with a Hamiltonian, we consider this little toy model. We have our superconducting resonator here and a standing wave inside. Then what we do is we place our artificial atom here at an antinode of the field. so that we maximize the interaction between the field and the qubit. And in general, such a system where we have a two-level system interacting with a field is described by the Jaynes-Cummings Hamiltonian. So you have the first term describing the photon. So you count the number of photons with frequency omega r. And then the second term is the artificial atom. So you have the sigma z, which looks if there's an excitation in the qubit or not. And it has a frequency omega a. And finally, we have the interaction term. So the strength of the interaction is defined by this G, the dipole coupling constant. And what you can do is the following. So you have sigma minus. You can annihilate the excitation from the qubit and create one excitation in the photon mode. Or you can do the converse. You can excite the qubit and destroy a photon. Now the key elements of this circuit QED setup are the following. So we have, due to the one-dimensional geometry of the resonator, a large vacuum field residing into it. And then, by engineering those mirrors, which are actually capacitances, we can achieve a high Q factor in the resonator, thereby confining the photons for a long time inside the resonator before they finally decay. Last but not least, we also have a large dipole moment of the qubit, which allows us to have a strong interaction between the qubit and the resonator. This is all made to achieve one go, strong coupling. So I should maybe go back and talk about what we're going to do with it. So here we have just one qubit in the resonator. But ideally, for doing experiments of all kinds, you might want more than one such device. So you could put one more here and one more here and consider transmitting information from this end to this end by the resonator. So you prepare your qubit state, couple it to the resonator so that the information flows from the qubit to the resonator, and then transfer the information from the resonator to the second qubit. So to be able to do such information exchange, we need to have a strong coupling between the two systems. That's why we need to tune those parameters in the right way. So that's the uncoupled energy level scheme. So here you count the photons with energy omega r when the qubit is in the ground state. Here the qubit is in the excited state. So this photon ladder is simply shifted up by the qubit frequency omega a. Now if we add interaction, if we add this term, and consider the resonant case when both systems have the same frequency, the energy level will change and will take on this form, which is sometimes called the Jaynes-Cummings ladder. So here you see the ground state. And here in the one excitation manifold, the levels are no longer degenerate. They will split up and be separated by 2 times the coupling constant. And in a 2 excitation manifold, the coupling is even bigger, the separation is bigger and gets a factor square root of 2. As you rise up, the coupling goes with square root of n. And this is a quantum mechanical feature of the system. If you were to couple classical harmonic oscillators, you wouldn't observe this increase of the splitting. If you want to see this in the lab, you need to go to the strong coupling regime. What you need to make sure is that this spacing here is larger than the line width of the lines you observe. So what we need to have is that the coupling is much longer than the decay rate of the qubit and the decay rate of the resonator. What you can also do then is, for instance, populate only the qubit and wait a little. So because this is then no longer an eigenstate, the excitation will go back and forth. So you start out by putting the excitation only in the qubit and nothing in the resonator. Now, because of the interaction, it will transfer after some time completely into the resonator, and the qubit will be in the ground state. If you wait for some longer, it will travel back and be entirely in the qubit. So what you can do in the strong coupling regime is you can observe the coherent transfer of excitation between the qubit and the resonator. Now I'll show you some experimental data finally. First one is the so-called Vacuum-Rabi splitting.
Before you do that, in the strong coupling regime, don't you really now have to worry about the fact that it is a Q-trit rather than a qubit?
Yes, indeed. So, well, a strong coupling, I would say, is still kind of fine. What is really, it gets really bad when you drive it very strongly. So what we want to do is, first, consider the simple case when you're not in resonance. So you have the resonator here, a certain frequency, and the qubit is detuned from it. Let's say it's higher up. So if we probe our resonator, meaning if we send a frequency, a tone of various frequencies through the resonator and look at what comes out, we expect to see only this line here, a simple Lorentzian line shape. This is what we actually see. So we see one peak, and this is the resonator frequency. Now, if we go back into resonance and tune the qubit so that it has the same frequency as the resonator, we get this splitting I mentioned before. If we measure it, we can indeed see it. So this is a previous peak from the resonator from before. And simply, due to the presence of the qubit, this single peak will split into two peaks, those two lines. And this is what's called Vacuum-Rabi splitting. Now we can do this in the time domain. So we try to observe Vacuum-Rabi oscillations. So we populate the qubit and wait and see where the excitation will travel to as a function of time. So in this plot, you see the qubit population on the left-hand side and the resonator population on the right-hand side. And on the horizontal axis, you have time. So at t equals 0, we put one excitation in the qubit. And we see that nothing's in the resonator. And then we wait for some time. Let's wait 5 nanoseconds. And then if you look at the qubit, we see that nothing's left. And the excitation will have traveled entirely into the resonator. And if we wait for some longer, well, the excitation will travel back to the qubit and have left the resonator. So that's the Vacuum-Rabi oscillations. Finally, a few words on how to operate the qubit independently of the resonator. So far we've been considering the case where both have the same frequency and interact very strongly. Now we also might want to address only the qubit and not worry about the resonator. What you want to do then is work in the far detuned regime. So you just make sure that the difference in frequency between the two is much larger than the coupling strength. Then you can take the Jaynes-Cummings Hamiltonian and simplify it. So you'll see that you still have the resonator and the qubit, but the interaction term has vanished. What you have instead is a renormalization of the frequencies of the two. This term is here. So one term is the cavity frequency shift. So this is my photon number operator, and the frequency is this expression here in the brackets. So you see that it's the original frequency, omega r, plus g squared over delta times sigma z. So what happens is that depending on the state of the qubit, the frequency of the resonator will shift by this amount, g squared over delta. What you could also do is take this term here and put it in front of the qubit. Then you could interpret this term as a qubit AC Stark shift, simply meaning that the frequencies of the qubit will shift because it's put in an electric field. the qubit frequency in itself is also affected. So you have the original frequency, but it's shifted by g squared over delta. This is a Lamb shift, simply because the qubit sees the vacuum fluctuations inside the resonator. And those shifts turn out to be extremely convenient. Now, if we look at resonator transmission again, as a function of the proton we send through the resonator, we will see that the frequency of the resonator will change depending on the state of the qubit. If it's in the ground state, we see one peak here. But if the qubit is in the excited state, the peak is shifted to this frequency because of this term here. And if the lines are narrow enough, what we do is we measure here what the transmission is. Now, if the qubit is in the ground state, we measure full transmission, and we know by measuring the resonator that the qubit is in the ground state. But if we measure here and get no signal at all, we know that the qubit is in the excited state. So we use this qubit state-dependent frequency shift of the resonator to determine the state of the qubit. This is what's called the dispersive readout. That's what it looks like in the lab. Main components is the dill fridges in red and in blue. This is actually the first ever cryo-free dill fridge which was sold to people. So,
I like the way you pronounce sold.
Yes, so it was sold cheaply, but then poor PhD students well, invested some time into getting it running properly. So, Then you see some microwave equipment here, and some computers used to generate signals and analyze the transmitted signals and do data processing. Yeah, that's the almost 360-degree view. Now, that was the first part. Second part, geometric phases. Well, it's a quite nice concept because when you think about it, it's pretty strange. You have something which doesn't depend on energy and doesn't depend on time either. And then people thought, well, it's insensitive to those quantities, so it should also be independent of fluctuations in those quantities and be robust. So we can use it for, say, quantum computations. So that's, I guess, how the interest in geometric phases started in this field. A few words on how they arise. Well, that's a normal Schrödinger equation. So take quantum system and have it evolving for some time t and look at its state after this time. So assuming you don't drive any transitions, the system will acquire some phase, which is the integral of the energy over time. This is the dynamic phase. If you make h time dependent, you could say, okay, I'll just integrate e of t, and it should work. But it turns out that if you plug this inside the Schrödinger equation, it doesn't work. So what you do is you say, okay, let's keep this because it's a good idea, but we add some extra phase factor to see if we can compensate for what's missing. And it turns out that it works. So now you have, when h is time dependent, you have not only the dynamic phase, but you have an extra thing, which is a geometric phase. I'll now consider a more specific example, namely the spin half particle sitting in a B field. That's the Hamiltonian describing it. Now we make it time dependent. So we make a B with changes with time. And we do it in such a way that it changes slowly and that it changes in a cyclic manner. So meaning that B after some time goes back to its original value. And we can, for instance, it's not a coincidence, but we choose a nice path like this. So we take our B field and have it travel along this line in some time interval. when you consider such a path, you can look at the solid angle it encloses. So you just project this path on the unit sphere and see what's the area enclosed by this projection on there. That's simply the solid angle A. Now Michael Berry has shown that the spin-half system, after such a B-field cycle, will have acquired a geometric phase which is half the enclosed solid angle. And this is really geometric. So it doesn't depend on how big your B-field is or on how fast you travel along. It really depends only on the enclosed solid angle. So I could make my path totally different, but as long as this area would be the same, the geometric phase would be the same. And this is really in stark contrast to the dynamic phase, where you just integrate the energy. Now in circuit QED, we don't have a spin-half particle in the B field. Well, we need to create those or find those. Spin-half particle is pretty straightforward. We just use the lowest lying levels of our transmon as a spin-half particle. We tune it to a certain frequency, say omega 1. The B field is a bit more intricate. We don't have a real B field, we have an effective B field, which arises when you drive the qubit with microwave radiation. So this is our resonator with the qubit, and we attach some drive, some microwave drive here, to the qubit directly. This drive has an amplitude omega, a frequency omega d, and also a phase phi. And we're able to control all those parameters. And you can show that a qubit driven by such a drive is described by precisely this Hamiltonian. So you recognize the spin-half particle in the B field Hamiltonian. You have the Pauli matrices and some effective B field. In our case, the in-plane components of the B field, omega x and omega y, are the two quadratures of the drive. So by changing the amplitude and the phase of the drive, we're able to control the B field in the plane. The third component of the B field is the detuning between the drive and the qubit. So by changing the frequency of the drive, we can change the Z component of our B field. So finally, to have our qubit acquire some geometric phase, what we want to do is simply engineer this path with our microwave drive. And then we're done. Now, I'm going to show you this path, but not in space, but rather as a function of time. So that's the two drives. So we put our qubit in the ground state, apply this microwave pulse, and then measure the state of the qubit at the end. You're going to say, wait a second, it's a global phase, you cannot measure it. Yes, I cannot. So we add some pi-half pulses at the beginning and at the end of the sequence. So it's then a Ramsey interferometric experiment, which allows us to read out the global phase, the relative phase between the ground state and the excited state. But we're still not happy, because here we have some geometric phase, but also dynamic phase, which we're not interested in. So we want to get rid of it. What we do is we repeat the experiment a second time. So this is one of those circles with the B field. We do it again, but in the other direction. What will happen is that the geometric phase changes its sign. So we have a minus here and a plus here. And the dynamic phase keeps its sign. So that when you do a pi pulse, in the middle, the dynamic phase just drops away. And what stays is only the geometric phase. And because we want to reconstruct the state of the qubit on the Bloch vector, what we actually do is we perform state tomography. So we repeat the sequence, measuring each time a different component of the qubit, and then finally have determined its location on the Bloch sphere, from which we can extract the phase. That's what it looks like when you measure it. So we want to check this dependence. We want to see if the geometric phase is actually half the enclosed solid angle of the B field. So here you see the phase as a function of the enclosed solid angle. So what we do is we do many of those sequences, but change the amplitude of the pulse, thereby changing the enclosed solid angle. This gray line here is the theory prediction for a perfect two-level system. The green dots is what we measure. So you see that it's quite okay for small solid angles, meaning small drive powers. But then you see some discrepancy. And we were able to explain it. What we did is we treat the higher levels, which are there in our non-perfect qubit, and we include them as a perturbation to the two-level system. And then you can do some computations and find expressions which describe the influence of these higher levels on the geometric phase. And if you do this, you get this line, and you see that it agrees very well with the data we recorded. But this brings me to the conclusion. So we've used the circuit QED setup to measure the geometric phase in a multi-level system, and we've observed and quantified the deviations caused from the two-level geometric phase due to the higher levels of our qubit. In the meantime, what we've also done based on this experiment is seen if geometric phases, due to an independence of time and energy, are really robust or not. So we've taken this B field and added some noise to it with various intensity and various spectra, and seen if the phase stays constant or if it starts changing with the noise. And our conclusions so far indicate that indeed the geometric phase is robust, and more so than the dynamical phase. Another direction we've been exploring is the non-adiabatic phase. So what I've been doing, or what I've been talking to you about here, was the case where you move very slowly. And ideally, you don't want to do that because your qubit will decay. So you want to be as fast as possible. So you can do geometric phases which are faster, and then they're non-adiabatic. And what you can also do, and this is pretty cool, is not only acquire a phase, but acquire a matrix-valued phase. So instead of changing the global phase of your qubit, you also change populations. This is then called non-abelian. And as future prospects, we're considering to measure vacuum-induced geometric phases, whereby you use the vacuum field in the resonator to have the qubit acquire some geometric phase. And if things go well, we might want to build a universal set of quantum gates for which we need a 2-qubit geometric gate. And if we have this, well, we can consider dabbling with simple algorithms which are based purely on geometrical phases. So I'd like to thank you for your attention, and glad to respond to any questions if you have some.